Clarifiers are designed to physically remove solids that settle to the bottom or float to the top. Sedimentation and flotation processes take place in circular or rectangular clarifiers, which are also called settling tanks or sedimentation tanks. In fact, sedimentation is the principal basis of clarifier design. A typical plant may have clarifiers located at two different points. One that immediately follows the preliminary treatment process called the primary clarifier, and the other, which is known as the secondary or final clarifier. The most important function of the primary clarifier is to remove as much settleable and floatable material as possible. The purpose of a secondary or final clarifier is to allow for more pollutant to convert to settleable forms of biological solids. This is important because organic settleable solids can cause a high demand for oxygen, BOD, during the treatment process and/or to receiving waters. The flotation process removes fats, oils, hair, and other lightweight materials, such as plastic, to prevent damage to pumps and pipes further down the treatment process. This also helps with the appearance of treated effluent that's being discharged into receiving waters. The tendency of particles to float, and the rate of settling depends on the weight of the particles in relation to the weight of an equal volume of water, the size and shape of the particle, and the temperature of the water. Organic solids are rarely heavier than water, therefore they tend to settle more slowly. In regard to particle mass, primary sludges are usually denser, heavier, than secondary sludges. Particle settling and flotation rates also varies with the flow rate through the tank during the day, also known as diurnal, daily, variation. Factors that influence settling characteristics. 1. Temperature in general. As water temperatures increase, the settling rate of particles increases. As water temperatures decrease, the settling rate decreases. This is because the properties of water change with temperature. Water molecules expand as temperatures rise, and water molecules contract as temperatures decrease. 2. Short circuits. As wastewater enters the settling tank, it should be evenly dispersed across the cross-section of the tank and should flow at the same velocity in all ends towards the discharge area. Example: if the tank has an area of higher velocity, particles inside the tank may pass through without having proper time to settle out. Short-circuiting may also be caused by turbulence and stratification of density due to temperature or salinity. Example: temperature layers can cause short-circuiting in a settling tank when warm influent flows across the top of cold water. 3. Detention time. As wastewater passes through the settling tank with varying flow rates, the tank size should provide for any given volume to remain in the tank long enough to allow for sufficient settling. The relationship between detention time and particle settling rates is important. Most engineers design settling tanks for 2 to 3 hours of detention time. 4. Weir loading rate. Wastewater leaves the clarifier by flowing over weirs and into effluent launders, or other weir arrangements. The number of lineal feet of weir in relation to the flow is important to prevent short circuits or high velocity near the weir or launder, which might pull settling solids into the effluent. 5. Surface loading rate. In many plants, the surface loading rate has a direct relationship to the settleable solids removal efficiency in the settling tank. It's not uncommon for small activated sludge or oxidation ditch plants to omit sedimentation and clarification. Solids that settle to the bottom of a primary clarifier are usually removed by mechanical devices into a sump in the middle or at one end. From the sump, the solids are pumped into the sludge handling or sludge disposal system. Skimmed solids may be buried or disposed of with material cleaned from the bar screen, incinerated, or pumped to the anaerobic digester. Skimmed grease solids from primary clarifiers are often pumped to anaerobic digesters because fats, oils, and grease, FOG, contributes to biogas production. However, these solids can also cause difficult operational problems in digesters. Proper disposal of skimmed solids is guided by state and federal regulations, and can vary by regulatory agency. Thanks for watching, and don't forget to hit that like or subscribe button.